Okay, so I was a little confused about one of the problems here because it's something that no one got right, and I don't understand. I'm trying to understand like why no one got it right. So maybe I'm wrong, or maybe the question is confusing. So on this problem right here, so you have like an easy part and a hard part. Well, the hard part is relative, right? I mean, it's not hard. I mean, it shouldn't be hard. Okay, so on this part right here, it says, so you're given a filter, and you're given what the R's are, and you're given what the frequency is, and you're supposed to determine C1 and C2, and also the cutoff frequency, and you're given that you have a maximally flat response. So I think most of you got this part right, where the maximally flat response was this right here. So that told you what the value of the quality factor was. So that defines that quantity. The frequency defines this quantity right here. And so you know what the R's are. So you only have two unknowns right here and here. So here are your two equations. So this is all that's required to solve the first part. And then the other part was for the cutoff frequency of this flat response right here. And so my thinking is that the cutoff frequency is like 3 decibels down from the max, right? So that's 0 right here. 3 decibels down from that will be like 3 decibels or negative 3 decibels, which is so your amplitude is just reduced by a factor of square root of 2. And so this equation right here is this line, right? So you set this equal to 1 over square root of 2. And then that frequency that is the only unknown that you solve for. So you're left right here with one equation, one unknown, which is the cutoff frequency. Now, first of all, is that okay? Like, do you guys agree with that? No one? I mean, should it be something else that I'm not seeing? I mean, am I okay?
I'm not sure yet.
Honest answer. Okay. Yeah, so I don't know how to treat that question. Like, if no one got it right, that kind of worries me. That I mean, if I'm okay with this, with this kind of idea, then maybe the question's worded kind of funny, right? Or I just don't know.
Dr. Clark?
Yes.
I'm sorry to say this, but I think it probably just reflects a fundamental misunderstanding of the question by the whole class, because with these kind of questions, when you give us this many equations, I can solve this problem without knowing anything about the question just by the information you've given us. I mean, this is an exercise in algebra at this point almost, so that's just kind of what I'm seeing, like why I missed it, because outside of that, there's not a whole lot of prior knowledge required to solve this kind of question.
We also have the cutoff frequency in the practice test.
What was that?
You didn't say the cutoff frequency in the practice test?
Oh yeah.
That's what threw me off, I think, because we didn't really check for that.
Yeah, that's like one of the. Yeah, like how close to the practice test should the exam be? Like should it be exactly the practice test, or sort of like it? So, well, okay. So the reason I thought this would be okay is because on the last exam we covered these kind of problems, like trying to find the cutoff, right? That's why I thought that everyone would be okay with it. I mean, do you guys remember like going over that on exam 1? Like okay. So, granted, we haven't seen it since exam 1, right? Like we haven't had to deal with cutoff frequency.
So what is the cutoff? Like,
Oh, yeah, the cutoff is this equation right here. I mean,
so could we have just written that as our answer?
oh yeah, you guys, yeah. Yeah, I don't know if you missed it, but how I grade my exam is like for most problems, I'm not like really looking for a numerical answer. I'm looking for a proper setup. Okay, so as long as you guys set the problem up like this right here, you don't see me solve for C1 and C2 because that's just basic algebra. You guys know how to do that, right? I mean, sometimes you make mistakes, but that's not what I'm looking for. I'm looking for, can you guys, take these equations, reduce it down to like something like this, 2 equations, 2 unknowns, and that's enough. This equation right here was reduced down to this 1 equation, 1 unknown, and then you can stop here and go on. And you guys can do that with all your equations, okay? I mean, every single problem, you can do that. It's very rare that you have to like actually find the value. When you do, I'll try to make that really clear, but I don't think there's anything like that on this problem. I mean, on this test. Well, yeah. So. I just don't know how to deal with that because, like, well, okay. Well, let me give you another example of this. Like, for example, on this problem right here. So, I didn't really solve for the numerical value of omega, but I got it into a form where I can easily see, like, okay, well, if omega needs to double, then that means that R needs to be cut in half. And that's enough, right? That's all you need to do. Now, I don't recall anyone that had a problem completing the exam. I mean, sometimes a question was skipped, but it wasn't like people didn't get to the bonus. Because I think most people got to the bonus. But yeah, I've seen lots of people do lots of work and lots of writing, and that's fine if you can finish the exam. But just remember that I'm looking for how you guys are thinking about these problems, and once you get enough information, then that's all you really need. I'm not really grading you on your algebra. That's what I'm trying to say. And actually, most of the solutions are all symbolic anyway, right? Now, for those of you who did not do as well as you liked, or as you wanted to, on this exam, remember we do have the final. So study this exam very well, study the first exam very well, and then come back really strong on the final. Because the final is going to cover the same concepts. Okay? You guys see any issues that we can talk about, kind of quickly about this exam?
Can you do the small signal model equivalent circuit?
Oh yeah, right here. Yeah. Yeah. So remember, the small signal is just converting everything to a linear system, and that linear system is like the voltage controlled current source, our current controlled voltage source. That's all this is right here. And the reason why is because remember on that plot, if we were going to plot this right here, the system was like this. Right? Where we found the Q point and we tried to linearize it about that Q point right here. And so you can only go up and down in this range, and that's about it. Okay? But that's like the full nonlinear model. That's the whole transistor. But if we go to small signal analysis, where you're only perturbing a very small amount around there, then you can say, well, my whole thing is actually just, this whole thing right here. And that is a linear component, a linear element like that. That is a linear element. That's not a nonlinear. The current right here is proportional to the voltage by this transconductance GM. So a linear line right there. And that's what you're doing. You're still only, oscillating it around this point, but you're going to model it as a nice linear type of model. And that's the only reason for doing that. Well, there's other reasons too. There's other approximations that you're making too. But that's a small signal model right there. And yeah, so a lot of the analysis in looking at, not just transistors, but a lot of things in electronics, people try to linearize it. And that's where these equations right here come from. Right here. Like the Y parameters. This right here could represent a very complicated system, right? With all kinds of things in here, all kinds of elements. And what you try to do, you try to linearize it and say, well, regardless of what's in here, I'm going to treat it like a black box and treat it with some type of input resistance that we see, some type of output resistance that we see, and the relationship between the input and output are given by these voltage-controlled current sources. Okay. So, but this right here is sort of like a small signal model, right? Because you can't go too far, otherwise you'll experience some nonlinearities. And these elements right here, at least how we're modeling it right here, is a linear element. The current is proportional to voltage by this constant value right here. And we're not saying that G1 is nonlinear. We're assuming it's a constant value, so it's linear. So that's done a lot in electronics. Of course, there's sometimes you want like a linear circuit. a nonlinear circuit, because maybe you want to look at chaos, or you want to look at just various types of things. But what else did I see that I had a lot of trouble with? People had a lot of trouble with this right here. Okay, and and so like in the practice exam, you didn't have this, right? All you had was this and this. But this right here, this is a voltage follower. So no current is going through here, no current is going through there, right? So this voltage is just being copied, this ideal being copied over there. Now you can have current go through here and go in the nodes here, which is the same thing as the current going through over here. Now this resistor is irrelevant. Oh, I can also cross off this one too. That's irrelevant, right? Yeah. So otherwise, without these resistors here and this element right here, it'll be just like the practice exam problem. And in fact, the solution is exactly the same as the practice exam solution. Let's see what else is. I think most people got this right here. Everybody got that. Yeah, we already know that one. Most people, this is interesting. Most people got this right. In fact, I think everyone got this part right. But this part right here, some people were plotting voltage as a function of time instead of the voltage transfer characteristic, which is like input-output, not something as a function of time. So you may have lost a point or two, from that. But, I think that's. Oh, this right here. I threw on a differentiator, but you could have thrown on a capacitor. And in fact, that's probably even easier to throw on a capacitor for just getting your DC. To eliminate your DC. So if you just do it on a capacitor, you got full credit. People, try other things. So it's not like you have to do it, one particular way. Just try to. Oh, and the reason why this right here is okay for the for maybe the exam, but it's probably something you want to be very careful about in practice, is because, as we said in class, if you have a noisy signal coming out of here and you differentiate a noisy signal, it's going to look at the slope of all your noise. So if this was like some noisy sinusoid right here, it wouldn't come out as a smooth sinusoid. It would be all over the place. So in practice, you want to maybe filter your signal before going through here, or use another method, but just calculate. Yeah. So other than that, but like I said, for those of you who want to try to do really good on the final, then just study this very well. Same thing with exam 1, and then try to turn your weaknesses into strengths and come back.
There's still an exam 3, right?
Yeah.
Oh no, you just kept saying if you want to.
Oh yeah. Yeah, I don't want to give that impression there's no exam 3 yet. There is exam 3. Yeah. I'm assuming everyone does well on exam 3. It's only exam 1 and 2 you gotta worry about. Okay, so any other questions before we do the lecture? Okay. Okay, so continuing on, we're on lecture 29. So we're just going to continue on where we left off, and basically we were going through these types of families of amplifiers, these transistor families. So we're going to talk today about follower circuits, common collector, and common drain. Okay, so let's look at the terminal voltage gain, okay, AVT. Okay, so to find the terminal gain, which is AVT, for a common collector, CC, and common drain, CD, those kind of amplifiers, let's replace this bipolar transistor by a small signal model and assume that we can neglect, this little typo there, assume R0 is neglected. Okay, so basically, when we convert this bipolar part to small signal, this becomes linear, and really there's like this R0 there, but we're going to neglect that, and now I'm explaining why in a second. Okay, but and also, so this over here is the FET part. Okay, so this is the BJT, here's the FET, or this is the CC, the common collector, here's the common drain. Okay, and there's like a nice relationship between the two. Like whatever you do to this, you can easily convert your equation to this by just assuming your R pi and your beta 0, your current gain, they get very large, like they just go to infinity, and then that's the equation you get from over here. From over there. So in this case, we're going to convert this to this right here, okay? And in doing so, we're going to look at voltage V0 and voltage VB. Okay, so voltage V0, of course, is right here, and voltage VB is like right here. Now, the ratio of these two, output over input, that is this terminal gain that we're trying to look at right now. Okay, so this V0, you can just figure this out by Ohm's law right here. So, that's this current coming in right here. So this is a current controlled current source, okay, and it's proportional to this beta 0. So it's coming in this way. This is IB coming in this way, and so this is all the current going through here, right? It's going through this across this load, and so that's the voltage V0. For VB right here, you have this current, right? Well, that's here's your VB, right? And so you can think of it as like maybe KVL going around this loop. So you're going uphill some VB, you're going downhill some R pi IB, and then you're going downhill this amount times RL. So that's what all this is right here. So you went uphill this, downhill that, okay? And since you have all these, well, these two IBs here, you could factor that out right there. That's done by KVL. And then for this ratio, you take these two equations, and then you take the ratio here. The IBs cancel out, okay? And so this is your form you get. Now you can approximate this using this. Typically your current gain is much greater than 1. Okay, so that becomes insignificant here and here. And also your current gain is equal to your transconductance times your input resistance to your transistor. So if you plug those in to here, then you can get this expression right here. Okay, so yeah, because this beta 0, it becomes GR, so that's on top. This becomes beta 0, and this becomes GR. So you have all these R's, well, the R pi's on the top and 2 on the bottom, they all cancel out, and that's why you get a 1 here. And then these are left over, GMs. Okay, so this is the terminal gain for the common collector CC amplifier. Now for the common drain CD, here's the difference. You assume that your R pi and your beta 0, they get very large. Okay, so in that case, if they do get very large, they happen to equal what you get back here. So here, this was for CC, and this was for CD. Okay, so they just happen to equal the same values here. Now the thing is that it says for most designs, the common collector and common drain, if your transconductance in your load resistor is much greater than 1, then this one right here, adding to this large value, becomes insignificant. So this just becomes about 1 right here. And so this is so it's kind of interesting that your gain for both of those is about 1. So it's like your voltage, your output voltage just follows your input voltage. So the CC amplifiers, the common collector amplifiers, they're often called emitter followers, and the common drain amplifiers are often called source followers because of that reason. Now typically this gain value is between 0.7 and 1. Okay, but the reason why we can neglect that R0, which we did up here, so the reason we neglected that is because this value right here, which is about 1, is really much less than your intrinsic voltage gain. And remember, for the BJT, it was like 3,400. So if that's the case, that's one of the criteria where you can say, well, R0 is negligible. Okay, now let's look at the input resistance. Okay, so for input resistance, this is this RIB value. That B should be capitalized. So we're looking at this right here, looking at the resistance into the base, right there, the base terminal, the BJT. Okay, so we have this value which we see already. Okay, now this equation right here has both the VB and the IBs in it. Okay, so we're just going to take the ratio of that. Okay, and that's going to be your RIB. So you have your IB and your voltage across there at that right here. That ratio is your RIB. And we can approximate it to be like this. And that's doing the same approximation as last time by assuming that beta 0 is much, much greater than 1. And also that beta 0 equals GM times R pi. So we can filter out, factor out this R pi on the front. Okay. Now for the collector drain, the common drain amplifier over here, what you want to do is you're going to assume that, well, we already assumed that beta 0 gets very large, but also for this over here, the FETs, you also have to assume that R pi is very large. Okay, so the approximation here is that this RIG goes to infinity, and RIG is like right here. It's just very large, this value. Okay, and again, it's because when dealing with FETs, R pi is extremely large, and beta 0 is extremely large. Okay, but again, we've taken an expression for the BJT, and we just approximated the R pi and beta 0 getting very large, and then we get the value, the respective value for the FET over here. Okay, now for the overall input impedance. Okay, so remember, this right here is just for looking at the base. The overall input is right here. Same thing over here. This right here is looking at the gate. This right here is for the overall input. This resistance right here is like the resistance due to the source. So whatever source you're having in this system, that source also has a little bit of resistance. Okay, so anyways, that's the input. So in this case, for RCCIN, which is right here, that's just these two in parallel. You have your RB and RIB in parallel. So here's the RB, and here's the RIB. So these two things are in parallel right here. And same thing over here. This RCD for input right here is this RG in parallel with RIG. So that means that this piece right here is in parallel with this over here, as seen in that direction. Okay, so that's for the input resistance. Okay, now for the overall voltage gains for each one for the CC and CD. So for the CC, it's the output voltage, the overall output, and overall input. So this right here and that. We can separate these out. Now we've already figured out this right here. This was the terminal gain. Right here. That's what this was. This piece right here, we can figure that out with voltage division. And so this is what we get right here for the VB. So for VB, right here, that's just these two in parallel, right? And divided by those in parallel in this RIB. Wait, I'm sorry. It's these in parallel right here on the numerator, and that plus those in parallel on the denominator for the voltage gain. And this right here, this RIB, that was the R1, R2 when you're looking at your 4 resistor network connected to your amplifier. Because remember, this network is a small signal model. Okay, so that's why you don't see any capacitors there. And so this RIB, it took that R2 and R1, they folded them over, and so they're in parallel with that. This right here was a bypass. You're all familiar with that. Taking the regular model, converting it down to AC small signal model. I mean the AC equivalent circuit. Okay, so follower signal range. Okay, so since the emitter follower CC and the source follower CD circuits gains are about 1, then only a small portion of the input signal appears across the base emitter or gate source terminals. Okay, so these circuits can be used with relatively large input signals without violating their respective small signal gains. Okay, so we have this right here for CC, right here. So that's your VBE, okay, and that's just this IB times R pi right here. That's the voltage across here, here to here. Now, since this VBE, and we've seen this before, where it has to be less than 5 millivolts, then you can solve for this VB right here. So if that's going to be 5 millivolts or less, then you can solve for this by just taking everything right here, flipping it, putting it on this side, and this expression you get. Here's the 5 millivolts, and this expression, when you put it on this side, taking into account that beta is greater than 0, much greater than 1, and beta 0 is equal to transconductance and input resistance. You're going to get this expression. And the nice thing about this is that you can see that even though you're multiplying this with a really small value, this right here could be quite large, right? So since this could be really large, then that means that your V0, what was that? your VB can be actually larger than 5 millivolts, because you're taking a small value, but you can possibly multiply it by something that's much, much greater than the 5 millivolt. The 0.05 value. And that's the reason you can get around that. Okay, and for the CD, it's sort of the same, right? We've seen this before, that this right here has a limit of like 20% of this, right? And so solving for your VG right here, you're going to get this expression right here. And again, this value right here could be quite large, so you have lots of room, lots of freedom, large range for this. Okay, so let's look at the the output resistance. So the resistance, looking into the emitter terminal right here, that's looking in this direction right here. That's going to be your Vx over Ix. So here's your current Ix, here's some Vx. The ratio of that is going to be your RIE. Okay, so if you just do like your current KCL here, your Ix right here is going to be equal to minus I, which is right here coming in, and minus beta I, which is this current right here coming in, right? So all that has is something 0. And the I's, both of these I's right here, they are this Vx over R pi plus R theta. Okay, that's it. That's what this is. Okay, so it's this voltage right here divided by these two resistors, Ohm's law. Okay, so we're going to plug it in right here and plug it in right here. Okay, and then so once you have that, then you can take your Ix and your Vx, which you can factor out, and then that ratio is going to be your RIE. Okay, and then this expression you get from that, and then you can make your approximation by saying beta is much greater than 1, and beta is equal to Gm and R pi, then you get this expression. Now, this value right here is oftentimes much greater than this value. Okay, and if it's a lot greater, then you could just neglect this value right here. Now, for the FET model, again, if you just make these values get really big right here, and also your RPi, the thing is that this really gets small, and so this RIS can be approximated just 1 over GM. Okay. Oh yeah, that's what we have here. Okay, so so for the overall output resistance, okay, what we have here is the RIE, right? And we found out that it equals this. So your R output, your RCC, is your RIE in parallel with R6. Okay, and oh, I don't have that image here. Let me see. Okay, R6 right here. Okay, that's the R6 that they're talking about. So they're just in parallel with them. Okay, so that's where that came from. And again, you can approximate this right here as being negligible. So that's why this is like 1 over GM. And same thing with this. This right here is also like 1 over GM. Okay, so the book says that this is important to remember. Okay, that regardless of what type of circuit you're dealing with, if it's the CC or DD, the BJT or the FET, that your output resistance, your resistance, that you have from looking from the outside, they both look like 1 over the conductance. They both can be approximated as being that. Okay, so. All right, now for the current drain. We have here that, so the terminal current drain, the AIT, is the ratio of the current delivered to the load to the current supplied from the Thevenin source. Okay, so here's your Thevenin source, your Thevenin resistance. So is this current right here, is this current right here divided by this current? Okay, so that's what we have here. And now, the thing is that this current right here is actually this plus that, right? It's your beta, I, Thev, and this. And that's really I, Thev, okay? So, we just call both these as I right there. Okay, so that's what this is. Okay, so you can factor out I from both of them. And then since you're dividing by I, then you get this expression right here, okay, which is this beta plus 1. And then, of course, if you allow this to go to infinity, then you can get the expression for the FET, which is just infinity. Okay, and another way of getting at is assuming that the current is 1 going in, 0 going into the to the gate. The current going in here is 0, because that's like infinite resistance waiting there. Okay. Now, so in summary of the things that we just talked about right here, so the FET results in the table can always be obtained from the BJT results by letting R pi and beta 0 go to infinity. Okay, so here's what we have for this the common collector. Here's what we have for the common drain right here, and these results right here can be easily attained from these by making this approximation that R pi and beta 0 go to 0. Go to infinity. Okay, but it's nice to compare the two, right? Yeah, so we have the terminal current gains right here, the input signal range, talked about that. Output terminal resistance, very similar. Input terminal resistance, right here, is infinity. This right here was talked about in another lecture. But we also have the terminal voltage and signal source voltage gain for these two right there. So, in summary of your summary, let's look at the similarities and differences. So for the similarities, Both amplifiers provide a gain of about 1. So you have a high input resistance for both of them and low output resistance for both of them. And both can handle a relatively large range of signals, which is good. For the differences, the BJT has finite R pi and R beta, okay, and FETs have high values for this. But that means that for the FETs, they can more easily achieve high input resistance due to that because they have this high gate resistance. The BJTs, they can easily reach low output resistance due to a high transconductance, right? That went over transconductance value, GM. And this FET has infinite current gain as well. Okay. All right. So that's it for today. See you guys on Wednesday.